I'd like to announce that today, hello everyone. Today after the colloquium, we're going to have lunch with Roberto. So we'll be at 2 in the main entrance, just in case that someone else can join us. Without deciding where we do when we move. Also, Roberto will be here until Friday, so I organized 2 meetings. One it is for tomorrow afternoon, 3, and the other is for Wednesday, Thursday. No, Tuesday. Oh yes, today. Yeah. Thursday. Okay. Also at 3. The Thursday will be in the Halpha. So if anyone can join to the discussion, please come and present in Twitter. It will totally informal. So any question that you want to discuss related with galaxy evolution, with the Starlight, with the J5, J+, or Sloan, or any other Halpha, or any other where we will be happy to answer and I can help. Okay.
Okay. Well, this is on behalf of the directorate and also the Severo Ochoa Excellence Program Science Director, which cannot be here. It's a pleasure for me to introduce and welcome Roberto to the AIA and for this colloquium, for the Severo Ochoa colloquium. I may say many things on Roberto, but I prefer to say, he told me to be, concise. So what I say is that Roberto T. Fernandez is a PhD from the University of Cambridge in '95, some time ago. And currently he is a professor of astronomy at the University of Santa Catarina. And he has been, he's well known and expert in the field of astronomy, STARLIGHT astronomy, large database. Has been in many places around the world. I would just to mention a few, in the John Hopkins University, here. He has been here. He's a fellow actually of the AIA, and we are very proud of that. And today, well, it's important to say that he's teaching now physics and astronomy as professor in the university, and has been also a coordinator of the postgraduate program of the university for a year. And he is very well known, mainly for his interest in stellar population, galaxy evolution, large database astronomy, and so on. And in particular, I would mention for the code Starlight and its applications. That's one thing, but some time ago, but still. So, and now is have developed a synthesis code with Starlight for more than 1 millions of galaxies, I would say, which is a very strong merit. And today he's going to speak us to stellar population and emission line with S+, which is a project which is the start. Thank you, Roberto.
Thank you, Pepe. Thank you, everybody. Yes, that's good. So today I'm going to be telling about stellar populations and emission lines in galaxies, of course, but as analyzed with S+, which you may have heard about. For some strange coincidence, you have an identical telescope here in Spain. I don't know why. And this is really the work by Julia Thaina-batista. She's going to be spending some months here, starting in November, I guess. So I don't know what she's going to talk about because I'm stealing her work. So, okay. So before, where is my mouse again?
Yeah.
Okay. Before talking about that, I will very briefly talk a bit about stellar populations, emission lines, and S+. Okay, just a few slides to refresh your memory. So stellar populations, well, what is going to be the first half, the first few minutes is going to be about spectroscopy, spectral stellar population, then how we see that in photometry. So to build a spectrum of a stellar population, simple stellar population. This is from the famous paper by Conroy 10 years ago. It's a basic recipe which involves things that we know. The IMF, we know, or we assume an IMF, how many stars of different masses we have. Stellar evolution, here we have the HR diagram with isochrones from very young to very old populations, so that we also know. And we also know stellar spectra, how do they emit from lambda equals 0 to infinity across a wavelength scale. And you combine these three things, and you predict the evolution of simple stellar populations. Young stellar population, not so young, very old. Oops. And here we see this as an animation. What you're seeing there is the evolution of a stellar population from million years to giga-years. So it's a logarithmic clock. We have all 4 decks from a million. Nothing happens before a million years, right? It's just nothing happens. Everything stays the same. Then from a million to 10 to 100 to 1 giga and 10 giga. There are 4 decks of interval, and the spectra changes. And it's also, so it's a log clock, and it runs backwards because we're talking about look back time. So this is how we see it in spectroscopy, and this is how we would see it in photometry. Just 3 filters here, but just to give an idea. It seems like a lot less information, much less information. So I'm using to do spectroscopy. We're all used to doing spectroscopy, but now we have to do photometry. And the first thing we're saying, no, we're not going to be able to do the same. Let's test that in this talk. So here we have a bunch of versions of spectra for simple stellar populations of different ages and different metallicities from different people, including Rosa here from 2005. Boulevard Charlot, a very famous one, and others. There are other versions of this. So this is a main ingredient in any stellar population analysis. You have to know how a simple stellar population, say a cluster of stars, behaves as a function of time and metallicity. This is a very key ingredient. And once you know that, and there's been lots of progress in the last 20 years about this. Once you know that, then you can start playing games like this one, which is, here's a spectrum, it's in black with green, right? Green is for the emission lines, they're painted in green, but it's an observed spectrum from the Sloan survey. Then you can start mixing the spectra that I just showed you of different ages and perhaps different metallicities. According to some recipe, here is a non-parametric recipe, which puts some of the light in, or some of the mass or the light in young stars, some other in old stars, some other light in some other mass in intermediate age stars. This is a recipe, which is non-parametric. In this case, it could be a tau function exponentially decaying. That's up to you to choose. That's a star formation history. That particular one produces this red spectrum here. It's the sum of SSPs. So from that, you infer the star formation history. And if you subtract one from the other, you can measure the emission lines. So this is what I've been doing all my life, and I thought I couldn't do better. Yeah. I did. This is just, you cannot do this with photometry, or so I thought. And these are other examples of results that we got from, I'm using my own code to illustrate the sort of things that you can do with spectroscopy, but it applies to any other code, of course. It's the same again, spectral fits of using Starlight, my code, for galaxies of different masses. And here you have different star formation histories. Look back time, this is today, this is the past. And you see, just by looking at these 5 examples here, that these galaxies down here, they have a star formation rate has been kind of roughly constant across time, whereas those in the top are forming much more stars nowadays than they have done in the past. So that's what people have called double sizing, just with 5 galaxies. We did the plot for other reasons, and we saw we can see downsizing with those 5 examples. So just an example of the sort of thing that you can do. And we've been doing that for a long time. And from the emission lines, you can do a lot of stuff, of course, characterize AGN, start from metallicities, nebular extinction, etc. Just a couple of examples. The mass metallicity relation. What I really want to point here is this axis. This is a gas phase metallicity. Doesn't matter the rest, okay? We can only do that with emission lines. Yeah? So that's where emission lines are very important. So I'm not going to go into the details of these plots. That's not really what the talk is about. Now, okay. Can we do anything similar with photometry? And with S plus photometry or J plus photometry, or of course, J pass is going to be better, but it's the same idea. So we know, I don't have to explain it, I don't have to tell you anything about S plus, really, it's just, the picture is different, but the telescope is the same. So it's in the south, is a cousin, not a cousin, it's an identical twin, really, of J plus. And you also know the filter system, 5 broad bands and 7 narrow bands. The narrow bands pick, things like H-alpha, nitrogen as well, oxygen 2, and other features in the blue. And what maybe you don't know about S plus is that it's going well. It's about 2/3 done, so 1/3 left to be done. So this is the area which is being observed so far. The green dots, the red ones are still to be done. So it's about 60-some% done. Okay. And some results, just there's no time to discuss any of them. I wouldn't be able to do that anyway. Just to mention that there have been lots of interesting results on environments, some on the transients like GRBs and supernovae, and some on ultra-diffuse galaxies. This is a study in which I participated myself. Photometric redshifts, quasars, classification of quasars, blah blah blah. The stellar part has been very successful. Have been able to find a bunch of very low metallicity stars in the halo. So survey is going on. Okay. Well, let me come back to my question. Can we do extragalactic work similar to what we have done with spectroscopy with Sloan, Halpha, Manga, MUSE, etc., with 12 bands and a small telescope? Well, so is it really, the comparison is looking at this movie of these thousands of points to just a few, 1, 2, 3 bands here. You can see the evolution in color. So it's much less detailed, but somehow the information is still there. I hope to convince you of that. So this brings me to what is really the topic of this talk. The problem is how to estimate stellar population and mainly emission line properties out of S plus, J plus as well. And basically, the main problem is really to separate nitrogen from H-alpha because they fall in the same filter. That's a problem. Okay, so here you have an example spectrum. You have the synthetic photometry, and you see the H-alpha and nitrogen lines. They're all here. They all fall into this 660 filter. So can we separate them? So the rest of the talk is going to be how we tackle this with AlStar. Then the emission line based is really the new stuff, and priors. This is the trick. And simulations to test the idea and some results that we've gotten so far. This is, by the way, is all in a paper that was in Astro PH maybe 2 weeks ago or 3 by Julia. So, quick words about stellar populations in and emission lines with AlStar. Stellar populations part is really the usual stuff. No, nothing really new to tell you here. The emission lines is really the novelty. So AlStar is just like Starlight. Actually, the name AlStar is not tennis shoes or anything like that. It's the algebraic starlight. Okay, only one L. So it's algebra. So this is the idea. You decompose a galaxy or the spectrum of a galaxy or the photometry of a galaxy into stars of different ages. A little bit of the young stars, some other quantity of intermediate age, some other quantity of old stars, so on and so forth. And mathematically, this is a base there's the composition into a base plus an extinction term. So this is a population vector which tells you how much mass or light depends on how you do things. You put in populations of different age and metallicity, and these are the spectra that I've shown you before. Okay, the spectra that I've shown you before. This is a non-parametric decomposition. Please, please, please don't think that non-parametric means no parameters. It's the contrary. On the contrary, there are many parameters. Okay, non-parametric only means that I haven't postulated that this transformation history follows cosine, an exponential, whatever, right? That's all it means. There are plenty of parameters here. So there's a stellar base here and the emission line base. The stellar base is really the usual stuff. I've shown pictures of this before. There's a new version from some newer models by Sloan as well. So what you have are spectra for different ages, from young to old, and different metallicities. So we pick a set of this to represent the populations in the galaxy. In this example, in this work, I think we're using 80 components of 16 different ages and 5 metallicities. Of course, this is highly over-dimensioned, but that's not the problem here, okay? This works. This is just like the previous work we've done with Starlight and other things, and other tools as well. What is really new is that to that base, which is the stellar population base, stellar spectra, we're adding a bunch of nebular components to represent emission lines, possible emission lines in a galaxy, right? So, okay, we have the stellar part. Let's find now. We're going to put the spectrum to represent emission lines. How do I do that? One possible idea, and a naive idea, could be, okay, I'm going to have a spectrum which contains only H alpha. Okay, let's put H alpha, H beta, and the whole Balmer series together. And then another component is going to have only the nitrogen lines. And another one for sulfur, maybe another one for oxygen. That's a very bad idea. I can explain you why later, but it's a very bad idea. It's simple, but it's horrible. Because all the code does, sometimes it works, but the code only uses, when the lines are weak, the code uses these components to fit noise. You're always going to get a perfect fit if you do that, but it's meaningless, completely meaningless. So it's really good to have all lines together. So each of these is one of the components in a base, okay? Each component contains all lines, not only one. That's key. And these are the lines we were dealing with: oxygen 2, O3, nitrogen, sulfur, and the Balmer series. You can put more lines if you want, depends on the wavelength range. These are enough for S+ and low red. Okay, but how do we build this base? Where do I get this from? The idea is that I get it from nature, in a way, from Sloan. That's a way to guarantee that the emission lines that I'm going to derive, they're realistic. They may be wrong, but they're going to be realistic. I'm never going to find O3 over Hbeta of 1,000, because that's not in my base, right? So what I do, I use the BPT diagram, and 2H alpha, O3 H alpha is just a slight difference with respect to the true BPT, which uses Hbeta here. It doesn't matter because the lines here are derived, and we use H alpha because H alpha is going to be 1 for us. It's going to be unitary flux in our base, right? Just like a normalization wavelength. But this is really BPT, same shape. And we pick 94 components here. Just chop it into boxes, and for each box, we compute the average nitrogen over H alpha, average oxygen, average O2, S2, all these lines. And that gives me the fluxes of all the lines with respect to H alpha, which is 1. And with that, I build the spectra that I showed you before. Okay? It's completely, it's not really a regular grid, but it's nearly. And then we put some extreme points here to cover the area. Okay? So by definition, by algebraic definition, we're going to span this base spans this diagram, the volume of covered by this diagram. Okay, so that's what I mean that we're going to get realistic line ratios. So here again, unitary H alpha flux. I put I use Gaussians to represent the lines with 150 kilometers in sigma. It doesn't really matter. I'm not going to measure that with photometry. Although I know a way of doing that, but that's for some other talk. So here you have something which represents a metal poor H2 galaxy, metal rich star forming galaxy. Here in the bottom, massive spiral. Here a retired galaxy or a liner. There you go. This is what this base is doing. And here, but we don't see the spectra. I'm showing you a spectrum, but we don't see spectrum. What they're going to see are these points, 12 bands photometry, right? Which I have multiplied by 10 here, just so that you can see something. Okay, we're not going to see the lines individually, we're going to see these points here, right? These are the bands from S plus up to the R and 66, J6060. Okay. So I have not said anything about the colors in this diagram so far. But now I have. This is the logarithm of the equivalent wave of H alpha. This is going to play a very important part in this talk in a few slides. But not to this moment. To this moment, the equivalent wave is completely irrelevant. I have chosen a base which makes no reference whatsoever to equivalent waves. It's actually, they have infinite equivalent wave because they have no continuum, just 0, 0, 0, and the line is 0. Okay, the equivalent wave has played no part in defining my base, but it is going to play a very important part in a few slides for a completely different reason. Okay, and it changes from left to right. High equivalent wave, low equivalent wave, and we know precisely why that is so. These galaxies are forming stars. The equivalent wave is a proxy for the specific star formation rate, because H alpha is star formation rate, and the continuum is basically the mass of this basically specific star formation rate. And here you have retired galaxies and a few AGN over there. So we understand perfectly well how and why equivalent waves behave in this diagram. Okay. Okay, before I talk about equivalent waves again, let me just show you that these fits work. Code works well, very well actually. The example for an elliptical in Fornax. You're going to be seeing spectra here, but this is just a model. Try to focus on the points, the black points and the red points. The fit is the red, and the black is the observed photometry. Okay. If you cannot tell one from the other, it's because the fit is good, and in fact, it's better than 1% residuals. So excellent fit. No emission lines though. Maybe some weak H alpha over there, but very weak emission lines. This one is very different. This one is crazy. Yeah? Strong emission lines. You can see the emission lines on the spectrum, but remember, what you see really is the black points here. This is the observed, and you see that we're able to match it pretty well. Some little problem here around Hbeta, but again, 1% residuals, pretty good. In general, the fits are very good. Okay, not two more examples from Fornax. This is integrated photometry from these two galaxies. Well, sometimes the photometry doesn't help very much, but in general, the fits are very good, at least for the brightest galaxies. And it also works, especially, pixel by pixel in the galaxy, if they're big enough, they're close by. Like NGC 1365, we can do a spatially resolved study. What you're seeing here are, again, spectral fits to the spectral photo. How do I say this? Photospectral fits, photometric fits. I don't know. I have, I always said spectrum in my life. So there are photospectral fits to pixels. One in the nucleus, the other one there in the arm, another one over there. Okay, so we can do spatial. I feel like work with at least a few galaxies, though, just big galaxies. So excellent. The fits are perfect. The fits are very, very good, but that doesn't mean they're reliable. I can fit the data, and can I trust the results? That's the question we should be really asking. And okay, so let's do this. Let's try compare stellar populations and emission lines that we derive with those that we know. Okay, and what we're going to do here is going to use Sloan spectra, a bunch of Sloan spectra. I think it was 10,000 galaxies, uniformly spaced in equivalent to H alpha, just to give you an idea from very strong line to weak line objects. Okay, from the work by Ariel, previous student of mine, he's in Padua now. This is being analyzed with STARLIGHT, usual stuff, plus emission lines measured individually, basic spectroscopic work. Then to these galaxies, we're gonna do the synthetic photometry. We're gonna add noise, S plus like noise, which is larger in the blue and smaller in the red. It's about 7 times worse in the blue narrow bands than in the R band. I guess it's about the same in J plus, I haven't checked. Then we're gonna fit it, right? And we're gonna compare the input based on spectroscopy with the output based on photometry. So this is the paper there where I got the data from, Ariel 2019. He was analyzing the spectra of Sloan and galaxies as well. Galaxy is not important for what I'm going to tell you, but that's what he was doing, and that's where I get the masses, mean ages, metallicities, etc., and the emission lines as well. By the way, this work was kind of a follow-up, really, to a previous work done by Rafa Lopez Hernandez here a few years ago, still in the context of the Halpha survey, where he also used galaxies and fitted Halpha and galaxies at the same time. So, cool, that's me. Okay, let's go to the results. That's regarding stellar populations. Stellar populations as derived from spectroscopy, and here as derived from S plus photometry. Masses, ages, extinction, and metallicity. And direct comparison of the results. And really, we're really comparing spectra with photometry. At first, I was surprised, but not so much because I have done things in the past with Russell, compared different codes and different results. That was for JPAS actually, photometry, so more filters. But at first, I was a bit surprised, but this is really good, no? 0.2x uncertainty in age. Well, I'm happy with that. Masses, much better. Masses is always easy anyway. And even extinction, just 0.13 dispersion, that's pretty good. Even the metallicity, okay, there is an offsetting. But that offset, in fact, is not so important. That depends on how you define it. The fact that I can recover something which correlates with metallicity, that was kind of surprising, at least with optical colors. Maybe if infrared was covered, that wouldn't be so surprising. But anyway, this is not new, but it's reassuring that we can measure basic properties with a photometry. Now let's go for the tricky part, emission lines. And let's start with the good news. The good news is not surprising, but it's still good anyway. The sum of nitrogen and H-alpha, remember, H-alpha is surrounded by 2 nitrogen lines. They are all in the same filter for low redshift. So the sum of them, their combined flux, is extremely well recovered. What you have here is the log of the equivalent width of the 2 lines, 3 lines actually, together. Input against output, spectroscopy and photometry. And it's just 0.0 nothing. It's really excellent. Even when you're here, say here's 0, that means 1 angstrom. Even when the lines are weak, we know they're weak. We know they're weak. When they're strong, the dispersion is even less. So that's good. People in J+ have done this as well. It's with a different method, with 2 methods, a 3-filter method and a synthesis method. It's kind of the same result. It's basically the same thing. That's good news. But the bad news is that the ratio can be a complete disaster. You can do the sum, but the ratio can be a complete disaster. Not necessarily is, but sometimes or often it is. And this I have 2 BPT diagrams here to show you that. And here in blue are galaxies as they are observed in spectroscopy. And in red are the same galaxies with an arrow connecting them after my fit. Okay, so what's happening here is that the galaxy was over here, it was right wing, and it was converted to the left wing. Completely, by more than a dex. So the ratio is completely wrong. But the sum is completely wrong. Because we cannot disentangle. entry from H alpha. We know the combined flux, but not the individual, not the contributions of the two lines. You know, if you're right wing, you go to the left wing, that's good. That can be good, at least politically. But if you're left wing and you go to the right, that's even worse, right? Don't do that, please. You've been playing with this for a while here in Spain. Don't. I know what I'm talking about. So the problem, it happens both ways. So, and the reason is simple. Here we have three spectra, completely different NQ over H alpha, from 0 to a lot, really. But the same flux, the same total flux. And what's happening here is that we cannot distinguish only if this filter is three combinations. Or can we? Can we? Well, here's the trick. Again, I've been showing you this diagram for a while, and the color here is the key. Large equivalent with low, contrary actually. Low equivalent with, intermediate, large equivalent with. And that the equivalent with is something that we get from the fit. Not equivalent with of H alpha, as in this plot, but the equivalent with of the sum of H alpha and nitrogen 2. So when I plot this diagram using that combined equivalent with, and if it looks the same, then we have a way to solve this degeneracy. And this is the same diagram, but now plotting the combined equivalent with. I was calling it one, but one is another diagram which I invented myself. It has nothing to do with this, so Julia is calling it 1A. Anyway, it's the 1A. 1A is the BPT diagram colored by 1A, the equivalent wave of H alpha plus nitrogen. And what you see here is that the low, again, low and large, low and high equivalent wave. So again, this thing, I know, I can trust it to 0.000 dex. So if I do a fit and it puts my galaxy here, but it has large equivalent width, then I know I'm doing it wrong. I have to exclude these elements from the base and refit only if this start forming like elements. That's the trick. Okay, and I'm going to show in a minute that it improves a lot the recovery. There are other constraints. This is the first order one. There are other constraints in the line ratios themselves as a function of this thing. That remember, I know this. So if I know this, I can say, okay, my fit has to be between this here and there. So I can only use such and such base elements. So here's how the code works. I run it once with all elements, all the 94 emission line based elements, which can give me completely wrong results, except for the combined equivalent wave of H alpha and nitrogen. That's reliable. Then I use that to select which part of the base is more representative of those equivalent waves. And then I rerun the code. And this is just like seconds because it's algebra. It's not really minimization or anything. It's just, there's no numerics involved. It's just very fast. So let me see if I can make you understand how this works. So BPT diagram again. I'm going to fit a galaxy which is here. That's the spectroscopic value. Okay. In my first fit, it put the galaxy on the left wing, but it's the right wing galaxy. But then I realized, okay, the code gives me 5 angstroms. The observed one is 4, so it's good. A weak line, actually, the sum of them is 4 angstroms, so each of them is weak lines. So if I have 5 angstroms, then I cannot be here. 5 angstrom people do not live here. They live there. In fact, they live in this box here. So I redo the fit, but now throwing away all of these elements over there, just considering those in the box, and I get a fit over there. And you can see a little circle there because there's Monte Carlo simulations. We can do statistics, can do PDFs. So let me show you that actually. Same galaxy, we fit it up. After we restrict it, we fit it 100 times or 1,000, I don't remember. These are the 100 versions of the spectrum with the perturbations. These are the residuals, And this is what you get for the equivalent width of different lines from O2 to H alpha, etc. From each of the fits. Those are just the distribution functions, but they work like probability distribution functions. It's not Bayesian, is on the contrary, is very frequentist, but don't shoot me. It works fine. Okay. So, and here you have, for instance, let's see, H alpha equivalent width in this case is 0.5, so it's 3 angstroms. About 3 angstroms. This is the average in plus or minus. It's right on the spot. There are line ratios. Line ratios are more complicated, but just to emphasize that we have not only best fit, but some knowledge, some notion of the uncertainties involved. Now let's see a different example. This one is a star forming galaxy over here, which initially I thought was there. But my initial fit gave me 53 angstroms, whereas the observed one is 56. And 50-something angstrom people do not live there. Again, they live in this green box here. I redo the fit considering only this green points, and I get it over there, very close to the observed one. Well, that's kind of this is not Bayesian, okay? So it's not a prior in the strict sense, but it works like a prior. I have some prior knowledge which I'm implementing in my code to guide it, okay, to reduce the degeneracy. And it works beautifully, actually. I was surprised. To see how well it works. So here, what you have are input against output log equivalent widths. So weak lines, very weak lines, 1 angstrom, and strong lines, 100 angstroms. For all these different lines. O2, Hbeta, O3, H alpha, separate from nitrogen, and so forth. And if you see the dispersions, or they increase towards the bottom left, of course, it's a very weak line, 1 angstrom here. Yeah, O2 is even worse. Below 10 angstrom is already hard to fit very well O2. But you have an idea, we know when it's weak. Okay, it's not that you don't know anything, it's weak. But the numbers are really pretty good. About 0.1 or less dex uncertainty in the equivalent widths. And maybe you don't remember this, but this line is in a narrow filter. This one is in a narrow filter together with that one. But sulfur is not. Sulfur is not in a narrow band. Sulfur is covered by the R band, I think. And Hbeta is not in a narrow band either. So how am I fitting these lines if they're not in narrow bands? Narrow bands already hard enough. That's because we're fitting everything together. Right? We're fitting everything together. If we allowed for too much liberty on the, if we treated them independently, then we could fit them or not. Would be no. Would be just a matter of luck. Okay, some example results. To emphasize my main conclusion so far, so we can, with this prior, we can also recover the emission lines. J plus people, I think, what was the name? Logroño, something. Logroño, no? Logroño. They have done something similar with the 3-filter method and some other method, the synthesis, some kind of spectral fit they do, and they found that a way to recover or to improve the recovery of nitrogen from H alpha, separate them, is to use the G minus R cover. So if the galaxy is red, you correct your number towards one side. If it is blue, which is kind of what you're doing here, but not with the color itself, with the equivalent width, which is a more explicit, a more direct measure. So they are equivalent in a sense, okay, but this is a more explicit correction. So, okay, let's go for some results. Just to illustrate what we can do with this, we can do stellar populations and emission of work. So just to close, let me start with a few integrated spectra. Okay, again, it's work by Julia that I'm presenting really. To fornax, no, fluxes magnitudes. I don't know why people insist on plotting spectra in magnitudes, should be forbidden, but I know Rosa likes it, so I plotted it. And I'm still spectroscopy, sorry. I'm doing photometry, but in my heart, I can only see things this way, All right, so we have good fit again, 1.something% residual. It's a pretty weak, pretty faint galaxy. Another one. Oh, not the same, it's same spectrum, but early types. Fornax is full of early types. Well, every now and then there's something different, and this one, the photometer didn't really help, at least in the blue part. I don't know if I can trust that. So just to illustrate that, not everything is flowers, we know that. At least the error bars are telling me that there is something wrong, but AlStar forming one. And I think that for some weird reason, every edge-on system in Fornax has a nearby star. There's one there, there's one over there, another one over there. Some cosmic conspiracy. Okay, let me close by showing you results for the spatially resolved part of the work, which we can do for big nearby galaxies. So we're going to pick a typical example, meaning the best, of course. So again, example spectral fits for 3 different pixels, actually for noise zones, but with some Butterworth filtering. I'm not explaining all the pre-processing that we have done, but it's not so elaborate. It's kind of basic, really. But so don't try not to see the spectra, which I'm plotting here. What we're really fitting are the black points with the red crosses. So if you cannot tell one from the other, good. That means that the fit is good. So this is our data cube, 12 layers only, not thousands as we had in Halpha, but 12. And these are maps of, again, masses, well, mass surface density, so solar masses per parsec, per square parsec. Mean age from 10 to the 7, some 30 million years to about 10 giga. You see the young stars along the arms and in the nuclear region. Lots of star formation in this galaxy going on in the middle. The equivalent wave of H alpha, again, large in the H2 regions, in the nuclear part, low in this region of the bar. And the dust, plenty of dust actually, in the central part of this galaxy, which also harbors an AGN, by the way. We're going to see this in a minute. So there's also an interesting exercise you can do. Here's the image of these 3 filters combined into an RGB composite. But we have the dust map as well, so you can dedust the galaxy. If you take the dust and you believe the correction, that's how the galaxy would look like, right? Which I guess is, I don't know if that's useful, but it's pretty. There's the whole dust lane in the nucleus goes away, and you see star formation is clearer. There's a lot of star formation going on there, but the colors don't really tell you that because there's a lot of dust. What else? Fluxes in old populations, young populations, intermediate age populations. We can do this game. You see here the young population in the middle, surrounded by some intermediate, and along the bar, an older population. Everywhere else, there are old stars everywhere, of course, but the young ones outshine them easily along the arms. And you can even try to do, color composites representing different lines. H alpha, O3, and nitrogen in RG and RGB. And you see pretty red. This is red plus blue, right? In the middle. So low O3, mainly because of extinction. And anyway, looks like a Halpha map, right?
Mm-hmm. Better resolution.
Better resolution. No vignetting, nothing like that. And this is really surprised us. This is a study by MUSE of the Venturi et al. A few years ago of this same galaxy. Of course, this is the nuclear part, 1 arc minute. It's that little box over there. This is O3 and H alpha. So, and O3 is in green, H alpha in red. That's from their paper. And this is our version based on S plus. We have a telescope which is 100 times smaller in area, 80 centimeters and 8 meters, right? And I don't know, 1,000,000 times cheaper, but better than that. Of course, resolution is not the same, but it's pretty. You can see the ionization cone here, right? Not bad. And even maps of individual nodes. This is the H alpha map. This is MUSE map, our map. You don't see the many details, but overall configuration is the same. The O3 one, well, this looks much prettier here than there, but you can tell there's something here, right? I don't know. You have to have some imagination to see a cone here, but whereas here you don't need the imagination, just see the cone. But anyway, you see that there's a difference in the distribution. Pretty good, I would say. And that's about all I wanted to tell you. So I presented you the code, which has some old parts, some not, it's not new, the stellar population part. And the emission line base, that's new. That's I presented this before here, but it's improved now a lot with the priors. The base itself is improved, and the priors have improved it substantially. I tried to prove that with simulations and the input and matching input and output, and the dispersions are very acceptable for photometry. Anyway, showed some preliminary results for Fornex, and so far so good. So of course this can be done for J plus, and for J pass, I think there's going to be much easier, of course. The one thing which I have not said is that this probably, very probably, I am not 100% sure. It goes. This doesn't work anymore for when H alpha nitrogen move out of the J660 filter. That's in my mind. But Julia has done some tests, and she says, "Oh no, it doesn't go completely wrong." Well, let's see. But anyway, in any case, with JPath we don't have that problem, right? It just moves out of one filter and go to another one. So I don't know. Plenty of stuff to do. That's what I wanted to tell you.
Thank you, Roberto. Time for questions. Rosa, will you manage the question?
Yeah.
No. Yeah. Please, people in the room, please speak loud so that people in Zoom can hear you. And people in Zoom, if you have questions, raise your hand, and we will open the floor to you after the questions here.
I have a question about the emission line database, just to check if I get the idea correctly. So you use information from one of the PPT diagrams, the one that involves the version with only H alpha. That involves H alpha, oxygen 3, and nitrogen 2. That's right? And then the equivalent width of H alpha plus nitrogen 2. And you show us in the examples how well are recovered oxygen 3, nitrogen 2, and H alpha. But I was wondering about the other emission lines that are assumed to be like in the mock samples that are sampled from that PPT diagram, because for instance, sulfur 2 emission lines can change quite a lot. When you have one galaxy in that region in the PPT with nitrogen 2, it can occupy a wide area in the sulfur 2 diagram. So you can have like different values for sulfur 2.
Excellent point. So we choose the PPT because it's the most informative diagram of all the diagnostic diagrams you can think of. But so for a point over there, the point over there, all these coordinates are specified, but not sulfur and oxygen, as you mentioned. So what do? I played a lot with this, and in the end, I ended up with the simplest recipe. Not that it cannot be improved, but I pick galaxies around this box, and I compute the mean sulfur 2 to H alpha. So this galaxy, this point here has only one value of sulfur to H alpha. It could have two. It could have a range. You could have not an. You could have, another axis here for S2 over H alpha or O2. I tried that and it didn't quite work so well. Well, it didn't improve things very much. There is one problem when you start to allow lots of liberty for these things. Say, for instance, that for each of these points, you allow three very different values of O2 or sulfur, doesn't matter. Very different, a very small one, a very large one, and a middle, one in the middle. Then what happens is that you're always going to fit perfectly the filter which has that line. Because you can use it freely to match noise. Maybe say if you're fitting a galaxy which has no oxygen, no O2, no emission, but you have an element in your base where O2 is 1,000 and everything else is nearly zero. Then you're always going to fit that flux perfectly because you're going to attribute whatever flux is there, even if it's noise, to a line. So for technical reasons, in the end, I ended up choosing the simplest version, just picking one value per digit. But you're right that there are variations. If I understand you correctly.
Yes, and have you tested like allowing it to vary in the range, like for instance, for one of the beams in the layer,
I have.
the average values of the sulfur to
I have.
and allowing the go to
I have made versions where we have two values of S2 or two values of O2, so larger bases with more dimensions. I mean, in the end, we ended up with the simplest one. Maybe for specific applications, it could be worse now. If you want to find some sulfur, if you're looking for supernova remnants, well, not with this spatial resolution, I guess, but they have high sulfur too. You can adapt the base to your needs. In fact, there are other things which you can adapt. For instance, the recipe that I used, the way I implemented the prior, it's not so good for secret galaxies because they can have large probabilities and be in the right part of the diagram. So if you know you're dealing with an AGN or you have some reason to believe that, you can do some other trick. Okay, but that also is another thing which can you can adapt your needs.
Congratulations, Roberto. This is a very nice work. I think you are doing much better than I did with machine learning. Let's see how it's coming.
I taught the machine. I taught the machine and she learned.
I wonder, are you using any constraint? Because when you have the star formation region, are you using any constraint in the wheel and width of H alpha with the young stellar population, since you have the ionization potential?
No, but that's doable. That's doable. So what Inés is saying here that I'm in the star forming regime, I'm here somewhere. There is a direct link between the stellar population, the young stars, and the H alpha. For every two ionizing photons, one will produce H alpha, roughly. Well, that can be done, but I haven't. So there would be a link between the stellar part and the emission part. I have done that in Starlight, but not here.
Another question. There was a plot where you saw the recovered stellar population parameters. And I'm surprised that the metallicity, well, we have like a little bias in the metallicity, but we don't have bias in the other parameters, but this is the generic, right? So we will.
Yeah, you're right, but it really depends on how I define metallicity there. What I'm plotting there, each little point is not one fit. Okay, I thought it would be too easy. If I pick the best fit, these are the spectra that I'm fitting. They are synthetic spectra. If I'm using the same base, that would be too easy. So I'm fitting the perturbed version. So what I'm plotting there is the median of 100 fits to the same galaxy. So that's an honest comparison. If I use a mean, it is better. The thing is that in metallicity distribution, because it's so uncertain, it's broad. Sometimes it has two peaks. When you do the Monte Carlo, sometimes it chooses this or that. So if I use the mean, the offset disappears. So I'm really not worried about that. Whereas for age is stronger, it's more robust. Mean or medians do not change very much. But you're right that in principle, if there is an offset there that should be compensated here in some other way. But I think it's more a technicality here. And in any case, I'm surprised it correlates with anything. I don't believe it's metallicity from spectroscopy.
Stellar metallicity.
Stellar metallicity.
There are two questions online. The first one by Ole Rizzo. So if you can unmute yourself, please.
Okay, thanks for the great talk. I would like to get it clear, please. So can we, if we apply empirical prior algorithm that you showed, can we use line ratios to diagnose the galaxies, to classify them with BPT or VHN diagram?
Yes, I was afraid somebody was going to ask that. Let me see if I find something here. I think the paper we have the plot. I cannot find it here. Yes and no. Well, you can trust N2 over H alpha. And let me go back here. Let me go back to, okay, you can trust the y-axis here. So that's already a good thing, very good thing. You know, if you're dealing with an AGN, a retired galaxy, or a star-forming region. OIII over Hbeta, the problem is that, you know, you have things on both sides which have the same, have star-forming and non-star-forming systems with the same OIII over Hbeta. So what I'm trying to say is that it improves a lot, but if you do a ratio, you're doing a ratio of two things which have uncertainties. But if you want numbers, there's a figure in the paper where we do the histograms for different line ratios of interest, N2 over H alpha, of course, then OIII and 2, that one that people use to diagnose, to estimate metallicity of strong line methods and others. And when the lines are reasonably strong, they're pretty reliable. But when you're dealing with a galaxy with low equivalent width, then, you know, as it's also true in spectroscopy. When your lines are weak, then the line ratios are not so reliable. But you really should look at the figure in the paper. It's one of the last figures in the paper. They have histograms of the line ratios.
Okay, thank you. Thank you for the answer.
The second question is by Alejandro Lumbreras. We don't hear you. I saw you unmuted yourself, but we cannot hear anything. Maybe you can write the question in the chat.
Can you hear me now?
Yes.
Yeah.
Okay. So thank you very much for the talk. It was very interesting. I had already looked at the paper, but I got a better view of everything now, a very clever way of dealing with the different line ratios. I am one of the J+ people, for those in the audience who may not know. And I wanted to ask something and point out something, I think, about the magnitude, or let's say the flux, the assumed flux in the first part of the comparisons when you're dealing with your simulated data and you're comparing how can you obtain the emission lines equivalent widths and comparing with the the S+ simulated data with the spectroscopic results. And I wanted to, I think, reassure a bit Gines, if he was the one who spoke, I believe, that you are assuming a signal to noise of 50, if I believe.
In the R band.
In the R band. But to what flux or magnitude does this correspond in S+?
Whoa. Magnitude, what's that? Sorry. That was a typical number for the nearby galaxies that we plan to apply this to. You cannot go very far with this because of the redshift. If you redshift the nitrogen and H alpha out of the band, then things will go crazy. So that was
Okay.
kind of typical. And we have done the simulation for 25 as well. Remember that it's 50 in the R band, but in the blue bands, it's 7 times worse, I guess. In noise, in signal to noise, it depends on the shape of the spectrum, but so we found that it was kind of representative of the sample that we had. But it was just a test sample, really. It was not, any complete sample in any sense. But we do have the simulation for 25 and also for 100.
Okay, because I was looking at your results and I was really amazed because the correlation, especially with the sum of H alpha and nitrogen 2, where you don't have to do anything else, was really striking. Like better than what I got, or better than what Rafa Logroño got before, or better than what even Ginés was getting with mini JPAS. And I believe the thing might be related with the signal to noise ratio assumed. I was seeing that Ginés limited it at 20, and I am looking at my results, and I don't almost have no galaxy at 25. I'm dealing with the signal to noise of around 10, and I think if you went down in signal to noise, that would help us also compare when we are trying to reach fainter galaxies.
Okay. Yeah. Okay. Yeah.
Mm-hmm.
In this sense, it will be very interesting to make a plot of the galaxy that you show the IFU result, plotting by the signal to noise of the Spectra, J Spectra.
Yeah.
To see what because they are very nice. This is very nice galaxy, and
Typical.
but of course the signal to noise will decrease with the distance to the center of the galaxy.
We did some pre-processing there, which I didn't mention. Just apply a Butterworth filter, which kind of reduces noise, and also some more noise in the outer parts. So that improves things a little, but going back to the point, I think we have not stretched them. We haven't gone very far in the noisy direction, the low signal to noise direction. That's probably worth testing it. But mainly because we're really planning to apply it to nearby universe, very nearby things. And to get nice pictures as that for 1365, maybe there are 3 or 4 more galaxies like that in our survey.
Well, another sample in the future. Also, probably you don't have any result from the MUSE, except the comparison, the quality, but if you have a quantity comparison, will be also very useful, not only the qualitative, which is
yes.
Great. But
I think that Amanda Lopez in La Plata is doing that. For forms, they have the Fornex 3D survey with Mark Sarzi and others, and she's trying to compare like zone by zone, pixel by zone, arc second by arc second, something like that. What we did visually, I think we have a picture. I have a picture here. Oh, no, it's not the one. It's not this one. Oh, this is a comparison of maps produced with AlStar and the 3 filter methods. The 3 filter method that the J+ people came up with. But what I'm just a second. Here, this is the one. So this is a MUSE map. Flux of matter 2 in units of something. It's a bit hard to tell, but visually comparing the figures, the fluxes are about right. You have to adjust for the pixel scale, etc. But to do a proper comparison, have to take the MUSE cube and do the proper analysis. And I think Amanda is doing that.
In that case, because the comparisons with the Sloan are really very nice, but after all, is the synthetic photometry, and the main problem that probably will have to compare the result is that the photometry the observed photometry will not really coincidence with any spectroscopy
Yeah.
data.
Yeah,
Or something.
well, in
So that-
summary,
that-
real life is hard.
That probably the limit of the equivalent width
In
you
practice,
can
yes.
use.
In practice, it's gonna be, yeah.
Something higher. But
Yes.
in any case, it is a really nice methodology to be applied to nearby galaxies. Another point is the resin that you are using the spectroscopy resin.
Yes, I need redshifts. I haven't said that, but I need redshifts. You know, when I got into this business, people told me, okay, we're gonna give you redshifts. Photos are gonna be perfect.
Right. And for the C, they introduce a significant bias.
And that's one thing we should do, not so much for this nearby one, because you know the redshift anyway. But for, you know, for samples of galaxies and other redshifts, we should include in our simulations the uncertainty in redshift. If it comes from photo Z, it might have a substantial effect in everything here, stellar populations and emission lines.
More questions?
I have a curiosity, Rosa, for
Yes.
Roberto. Roberto, should you, very next one, so should you have a bunch of money to buy one filter for S plus or J plus? Do you think with one, if you buy and design one filter can improve or perfection your, so is that one filter problem if you have money, or is not one filter problem more?
Well, I don't have that money, so that's a hypothetical.
Anyway, maybe
I
some,
don't know.
maybe somebody has, is Is
Imagine
it
that we are
possible?
going to give you the money.
is it possible or is not, it's not the question of adding one filter to the set?
I don't know, do we have a problem with the, what's the third filter? U, J something, third or fourth, third narrow filter. It's 4 in the list. I don't know,
It's
30,
four.
39 or something.
Mhm.
Is that bad in J plus as well? Because in S plus, that filter,
But I don't think so.
Well, the filtering the blue in J-Pass.
It's out of nowhere.
yeah, but there is one which is worse.
Yeah.
I think it's a third or fourth in the sequence. That one, you can see it, it's you can see it in by eye, I did PCA, you can see that sometimes it has only one component for itself,
Okay.
meaning that it wants to do what it wants to do, regardless of the others. So that one could be improved somehow.
Okay, this is correcting the.
But if I wanted another, I don't think.
But do you think
Any big-
adding one filter would improve significantly, or is not, it's not a problem?
I'm coming to terms with the realization that, you know, we always think Spectra are highly redundant, but I spent my life fitting answer by answer and being very proud of it. But now,
Okay, thank you.
maybe that was not so. In fact, there's a recent paper by this Spanish guy. And also Halpha as well. Well, sorry. I don't remember his name, but so, you know, information theory speculations and saying that, you know, apply to galaxy spectra, saying that there is not enough information, not much more information in spectra than in broadband photometry. So it's an information theory paper, which I have to digest, but I picked this sentence there myself. I picked of my recent experience. And disappointment, disappointed with it and happy on the other hand, because nowadays we have photometry. So
Okay.
when you only have spectrum, you're going to see photometry sucks.
Okay. There is more comment online? Yeah, any comment, question? Okay, well, remember that you want to enjoy us for lunch, we'll be 5 minutes before 2 in Delta to go for lunch somewhere around. Also that on Thursday at 3, we will meet at the Sala de Junta. Tomorrow we have also another meeting that will be in la mini sala de arriba. It's quite small, but if you are interested, we will try to put it there. Okay, thank you, Roberto, for the presentation.